Welcome to the first lesson of the second semester, Kinetics, and we're going to just dive right in, get started. So first of all, what is chemical kinetics? Chemical kinetics is going to tell us how quickly a reaction will occur. It will not tell us if the reaction is going to occur. That is thermodynamics. And especially when we get to the full unit on thermodynamics, it will tell us if it is thermodynamically favored or unfavored, but kinetics will tell us how quickly the reaction occurs. Some reactions are thermodynamically feasible or thermodynamically favored, but they are so slow that they are perceived to almost be not reacting. And so here's an example of a very slow one and a very fast one. Diamond decomposing to CO2 happens so incredibly slow that for all purposes we say that it does not happen, but it does in fact happen so incredibly slow. Whereas the formation of water is almost instantaneous. If you have, especially in the case of an acid-base reaction, when you have free hydrogen from the acid and free hydroxide from the base, it's an instantaneous reaction. So again, thermodynamics tells us if a reaction can occur spontaneously or if it's favored thermodynamically, and kinetics will tell us how quickly that reaction occurs. So factors that affect the reaction rate. These are going to be a plethora of multiple choice questions can come out of this little section because they're easy to ask on the AP exam. So the first thing is the nature of the reactants. Some reactants react in a hurry, others react very slowly. If you had to guess which one would be quick and which one would be slow, it's a pretty solid bet that the solids, no pun intended there, would react much more slowly than liquids or aqueous solutions. So if you think back to, say, sodium chloride, it is a solid. When it's in a solid state, it doesn't react very well, but when I dissolve it in water, now I have free ions that have already given and taken away their electrons, so they're going to react much quicker than in the solid form. So again, physical state matters a great deal. Consider liquid gasoline versus gaseous gasoline. If you look at this reaction, they both are a no reaction if I do them in the solid states. But if I was to put those in the water and dissolve them, then that reaction would happen very quickly, and I would get a precipitant of barium sulfate. The chemical identity, what is exactly reacting? Usually ions of opposite charge, of course, react very rapidly. Also, the more bonds reacting in a molecule, the slower the reaction. And that is because more energy is required to separate the molecules into their parts. Substances with very strong bonds, which is going to be a high bond energy, will react much more slowly. An example of that would be, well, I guess I left out the example. It's in your notes. Metallic sodium reacts much faster with water than metallic calcium because you have group 1, which are highly reactive, versus group 2, which is not as reactive. The second factor that is your concentration of reactants. It's kind of obvious that the more molecules you have present, the more collisions that occur, and the faster reaction proceeds. Thus, its rate is greater. Pretty simple enough on that one. The more stuff you got, the more collisions, the faster the reaction. Temperature, we talked about this earlier in the year, heat them up, speed them up. So if you increase your temperature, the faster the molecules move, the more likely they are to collide, and the more energetic those collisions become. That'll take us back to, remember in the beginning of the year, the collision theory. Those are also going to be some of the same things that are affecting our reaction rates. An increase in temperature produces more successful collisions that are able to overcome the needed activation energy. In general rule of thumb is that a 10-degree Celsius increase will double the reaction rate. It actually depends on the magnitude of the activation energy and the temperature range, but in general, if you're increasing it by 10 degrees, you're going to double your reaction rate. Surface area of reactants. The more exposed surface area affects the speed of which the reaction happens. Again, you have more collision of particles. Now, something that a lot of kids get a little bit confused about is surface area means you want very small particles, so that's where you want to crush it. So if I have a block of sodium chloride, like a salt block, or a salt lick like the cattle like to lick on, that is going to react very slowly as opposed to my table salt that I've crushed up into fine particles. It's going to react a lot quicker. Except for substances in the gaseous state or solution, reactions occur at the boundary or the interface between the two phases. So in other words, the exposed surface of the substance. This is why you want to crush it. So if I put a sugar cube in water versus crushed up sugar cube into tiny little particles, the water is only going to react with the outer surface level around that sugar cube, and then it's going to dissolve very slowly because it's got to react layer at a time. Therefore, again, greater the exposed area, greater the collisions, it'll proceed at a much faster rate. Coal dust is very explosive as opposed to a piece of charcoal. There have been cases of grain elevators exploding because of the very small particles of all the grain, and so you got to be careful when you have very fine particles because they're much more reactive. The next factor is adding an inert gas. An inert gas is the same thing as a noble gas, and it does not affect the rate or the reaction since it is not participating in the reaction mechanism. This is a classic gotcha on a test question, so make sure you know if they're adding an inert gas, it has no effect. And then, of course, a catalyst is increasing the rate of the chemical reaction due to the participation. Unlike other reagents, the catalyst is not consumed, therefore it can be used again and again. It may participate in multiple reactions, but the effect of the catalyst is going to vary based on other substances. Also, inhibitors are the opposite, which reduce the catalytic activity, or promoters, which increase that activity. And just to make sure you understand, the catalyst is not part of the chemical reaction, is not used up in the reaction. Usually, the catalyst is participating in the rate determining step, or the slowest step, which we'll find about when we get to reaction mechanisms. And then catalysts can either be homogeneous or heterogeneous. Homogeneous or homogeneous catalyst means they're in the same phase. So if I had two liquids reacting and I used a liquid catalyst, that would be a homogeneous catalyst. But if I had two liquids reacting and I used a solid catalyst, then that would be a heterogeneous. Okay? Homogeneous catalysts can actually appear in the rate law because their concentration does affect the reactions. For the most part, most of the time the catalyst does not appear in the rate law, but they can. So I don't want you to think they can't. It's just rare. The collision theory states that when suitable particles react and they hit with each other, only a certain percentage of those particles are going to have a chemical change. These are what we call the successful collisions. The successful collisions have enough energy, also known as activation energy. At the moment of impact, the Coulombic attractions between each bonded atoms and the shared electrons is overcome in the reactant molecules, thereby breaking apart the pre-existing bonds, and they form all new bonds. The results in the products of the reactions, increasing the concentration of reactant particles or raising the temperature, thus bringing about more collisions, and therefore many more successful collisions will increase the rate of the reaction. So, what are the essential components of the collision theory? First of all, particles must collide. Without collisions, nothing can happen. Okay? Second part, most often only two particles may collide at one time. Next, proper orientation of the colliding particles is essential so that the molecule can come into contact. Okay? So if I've got two negative ends of particles bumping together, that would not be a proper orientation. The collisions must occur with enough energy to overcome the electron-electron repulsion of the valence shell electrons, and must have enough energy to transform translational into vibrational. Okay? So that the electrons can rearrange and form new bonds. We talk about these as being effective collisions. This collision product is at the peak of the activation energy hump, which we'll see in a minute, and it is called the activated complex or the transition state. At this point, that activation complex can either still fall back down to the reactants and not happen, or it can proceed forward and form the products. I think that's a repeated slide. Sorry about that. Apparently I have two sets of repeated slides in there. Sorry about that. So here is what we were just talking about. Up here is the transition state, or the activated complex. And again, it could either proceed forward and form the products, or it could fall back down and go back to the reactants. Both are possible at that point. And some will fall back down, and some will proceed. Very few reactions, of course, if you've learned, are 100% to completion. Okay. This graph here is called a Maxwell-Boltzmann distribution. I promise you'll see, not promise, but I'm pretty sure you'll see something like this on the AP exam. And what it is only the number of particles that are in the shade or the striped line are the ones that had enough energy to recur. So if you can look at it, the vast majority of the particles do not occur. Now, a while ago we said if you increase the temperature, then you increase the reaction rate. So if you look at the difference between the T1 and the T2 line, the T1 is the temperature from in the first graph, and then T2, we heated it, it doesn't say how much, but we heated it, and you notice that the distribution becomes flatter and wider. And so then that means more particles would have enough energy to react. Okay, so that's how you read that. Again, remember, a general rule of thumb is that every 10 degrees doubles the reaction rate. So that brings us to what reaction rate is. It is the change in concentration of a reactant or product per unit time. So A, of course, is our concentration, so change in concentration over change in time. Remember, when we see that bracket around a substance, that always means concentration. Okay? If the rate involves a reaction, a reactant, they all involve a reaction. If it involves a reactant, we're going to put a negative sign. And the reason we're putting a negative sign is because as that reaction proceeds, then obviously the concentration of the reactant is going to decrease. So it's going to be getting smaller. If we're doing a product, then we leave it as a positive sign. Okay? So this would give us our average rate. Our relative reaction rate is expressed as the change of time, change in concentration versus unit time. You should focus either on the disappearance of reactants or the appearance of products, okay? And again, rate of a change in reactant is always going to be negative because it's decreasing, and the product is going to be positive because it's increasing, okay? So we consider this reaction for the decomposition of nitrogen dioxide, and this is what that rate would look like, okay? So the NO2, and you're going to use your coefficients, it's negative. The O2 and the NO is positive. And again, what this is saying is that NO2 is going to disappear twice as fast as oxygen will appear. Okay? And then the rate of the NO appearance will be the same rate at which the NO2 is disappearing. So we're going to write the relative changes in concentration of the products and reactants in the decomposition of NOCl. Okay, so we know that the coefficient, so it's going to be -1 NOCl. Oops, that does not look good. Over 2 delta T is equal to positive 1 concentration of NO over 2 delta T, which is equal to positive delta Cl2 over delta T. Okay? So it's pretty straightforward. Actually, a lot of times, this pretty straightforward one is the one that people miss, because we're going to go on and we're going to talk about things that are a lot more complicated to calculate than this, and then they forget about this easy exercise. So make sure you don't forget about this going forward. Okay? So instantaneous rate is, we compute the slope of a line tangent to the curve at that point, and the rate is equal to the negative slope of the tangent line. The rate at which the reaction is not constant but changes with time, because concentrations change with time. So we're only going to be working with rates that are initial rates. Okay, so we're going to ignore the reverse reactions, because it's just easy for us to work with the initial rates and see what happens. Okay, so we're going to do differential rate law first. Then we're going to go into integrated rate law, and then we'll do reaction mechanisms as the last part of this unit. So the bulk of this unit is going to be the rate laws and the reaction mechanisms. The differential rate laws, or the rate equations, are the easiest. Okay, and that is when you have a data table of concentration and rate, and then you're going to use table logic, or you can use an ugly algebraic method to determine the orders of the reactants and the value of the rate constant. We did do kinetics last in pre-AP. If you are a junior, you got a very light version of it during the quarantine. If you're a senior, you got a little bit better version, but it's been a while, so you may have forgotten. So we're going to just go through this really quickly, and maybe it'll ring a bell. It's not hard, especially differential rates. Okay? So for the reaction, A plus B yields G and H. You're going to have a rate that looks like this. You have rate is equal to K, which is a constant, specific rate constant, and then you're going to have your concentration raised to an exponent. Okay, so of course in the brackets recognize molarities of that, and then you're going to have the orders of the reactants. The orders of the reactants are going to be determined experimentally. Okay, the rate constant is going to have values that are different depending on the presence of a catalyst, a large K value, what is the order of the reactants, and that sort of thing. Okay, but that's the basic way it's going to look. So the exponents determine the order of the reactants. It's the sum of the exponents is the order of the reaction. So if I look at this example, I would say that this reaction is first order in respect with A, second order in respect to B, and third order overall. Those orders of each reactant are going to be determined experimentally. Okay, the units of K can be calculated by the reaction orders and the units on the concentration and rate. Now, units of K are important because generally, if they're asking you to solve for K, they're going to ask you for the numeric value and the units, and the units are usually a point by themselves. So, for example, if the rate is in moles per liter second in the above rate law, we can find the units as follows. So we had this rate law from earlier. We had rate is equal, we had rate is equal to K, and then we had first order A, and then B was second order. Okay, so that means that K is going to look like this: rate over A to the first and B to the second. Okay, and so if I put my rate on the top, and I'm just going to do units here, of moles per liter times second, that's going to be divided by moles per liter times moles per liter squared. So then it becomes moles per liter second divided by moles to the cubed, liters to the cubed. Okay? So what I see here, of course, is that this moles per liter is going to be canceled, and then these are going to be changed to mole squared over liter squared. Okay? So now, in order to put what my units are going to be, There's a couple of ways you can do this, but I'm going to show you the most common way. The most common way is I would say I've got liters squared times mole to the minus 2 because it's on the bottom times second to the minus 1. Okay? Another way you could do that is you could say molarity minus 2 seconds minus 1. That is also acceptable because molarity, moles per liter, is on the bottom. And then a third way you can do it is liters squared over mole squared times second. Okay? This way right here is the most common way you'll see it. Possibly this way sometimes. Very rarely we see it the other way. But if you did it the other way, you would get credit. Okay? All right. So let's move on from there. Now, the shortcut way, which is the best way, is that whatever your overall reaction is, your units are going to be one less than that for your molarities, okay? So in that case, the concentration, or the overall order was third order. So I would write it like this. Oh, third order, so I would say liters minus 2 times it's first day back. Liters to the second times mole minus 2 times second minus 1. That's the way I would write that. Okay? If it's second order, then it's just going to be liters times mole minus 1 times second minus 1. And then if the reaction is first order, then all of your moles per liter will cancel out, and your time, it would just be second minus 1 if it was seconds here. Here's what I need you to be careful for. When you see time, okay, I want you to make sure you are looking at that rate and make sure what the time is, because we tend to just do seconds, but sometimes it can be minutes and sometimes it can be hours. And so in that case you would have hour minus 1 or minute minus 1. But please pay careful attention to what that rate gives you. When they give you a rate, they're going to give you some sort of time, whether it be second, minute, or hour, but make sure you're using the right one, because I would hate for you to do the whole thing right and then you accidentally put hour when it was supposed to be minutes, and then you miss the point for the units when you actually knew how to do it. Okay? So I'm going to show you the easy way first. We call this table logic, and then I will show you the algebraic method. I used to do it the other way around. I used to do algebra first, and then it looked all complicated, and everybody got scared, and I was like, oh, it's actually really easy. Okay? And so I'm going to show you the table logic first. Okay? And so basically it's this. If you are doubling the initial concentration of a reactant and it causes the initial rate to double, then the reaction is first order. It's 1 to 1, double and double, so it's a first order. If I double the initial rate of the reactant and it causes the rate of the to quadruple, then it's going to be second order. Okay? And then if I'm doubling the initial and nothing happens to the rate, it just stays the same, then it's 0 order. Okay? And so we don't even put that in the rate law when it's 0 order. Okay? All right, so sometimes you have to play around with it. So the main thing you want to do when you're doing that is you want to find you look at your experiments, and then you want to find 2 experiments in which one of the concentrations is held constant and the other one's changed. Because if both concentrations are being changed, then you really can't tell how it's happening, to what's affecting the rate, okay? So I'm going to start with this one, and to me, when I look at this, the first thing I see is, oh, experiment 1 and 2, A is being held constant. Perfect, okay? And so I'm going to look at that and I'm going to say, okay, that's being held constant, so that's not affecting it. If I take this and it's doubling, so I multiplied it by 2, I increased it by 2. I need to get a different pen. Hold on. Okay, so I am doubling this by 2, and then my rate went up by 2. So that means B is going to be first order. All right, and so then I look to figure out what A is, and I see that in experiment 2 and 3, they have doubled A and kept B constant. Okay, so they doubled this, and then this went up by 4 times. Okay, so that means, since it quadrupled, that A is going to be second order. All right, and so here is how I would write that rate law. I would say rate is equal to K, and then A to the second, B, okay, and then the overall is third order overall reactant, okay? Okay, so if you needed to explain that on a test or a quiz or the AP exam, you can explain that by saying when B concentration was doubled while A was kept constant, the rate doubled. Therefore, it's a first order reactant. For the concentration of A, when we doubled A's concentration and kept B's concentration constant, the rate quadrupled. That would be indicating a second order for that reactant. So that's a way you could say that. Okay, so now let's try this one. And in this case, we only have one, so that should make it pretty easy, right? So when we double A here, what happened to my rate? My rate went up by 4, so then my rate would be rate is equal to K, A to the second order. And so then, of course, it would be second overall. Okay, now I have this one, A. It's a little bit out of order. Did I skip it? Nope. Oh, I skipped this one. Let me go back to it real quick. I'm sorry about that. No, I didn't. Well, I don't know where that one is. We may have to add it in. Sorry about that. So I have A plus B yields C. And so when I look at this, I say in experiment 1 and 2, when I doubled, so times 2, no effect. 0 things happen, okay? No effect. So that means A, we would call it 0 order, which means we will not be including it in our rate law, okay? Now if I look at A and held it constant for experiment 2 and 3, I see that I doubled and my rate doubled. So that means that B is first order. So I would write that as rate is equal to K, B, and that's it. So that would be first with respect to A, but first overall as well. Okay? There's the one I was missing. It's just not in the right place. Sorry about that. Okay, so in this one, I look at and I double A, and it doubles, right? Double. Oops. Double, and then double. So A is first. And then here, I don't have an A held constant. So what can I do here? Okay, so I look at, I'm going to change colors here so we can see this. I look at this one and it doubled. Okay, and I already know it's first order, so I know that it's going to double the rate. But then when I also double B, the rate still only doubles. So that means that B is going to be 0 order, okay? Because if they had both been first order, you would have had a doubling for the first order of A, and you would have had a doubling for B. But because you didn't have any other effect, that means that A is first order and B is going to be 0 order. So I would write that as, again, when something is 0 order, we leave it out of the equation. And then that would be first overall. Okay? All right, so that's how you do the table logic, okay? Now let's actually use some numbers here and figure out what we're doing here, okay? So we're going to determine the rate law on this one, and so I'm going to look at that and I'm going to say, okay, let's figure out the NO2 minus, because the first 2 experiments I have the ammonium single, okay? So I'm going to figure that out, and I'm going to say that this is doubled. That's times 2, and then the rate also doubled. So I know that B, not B, we're not doing those anymore. So I know that NO2 minus is going to be first order. So I'm going to leave it like that. And then in the second and third experiment, the NO2 is held constant. So this one is times 2, right? And then the rate also times 2. So NH4, also first order. So that's going to be rate equal to K. So that is how we're going to do that. Now it wants to determine the value of K in its units. Okay? So honestly, it does not matter which one of these experiments you pick. You can pick any of them. I usually just pick the first one to make my life easier. So when I'm dissolving for K, it's going to be rate over the concentration of each one of those ions because they're both first order. So I'm going to type that in, 1.35 times 10 to the negative 7, and that's moles per liter times minute. So there's an example of watch your time. And then I'm going to type in the concentration is 0.100, and that's going to be moles per liter. And then 0.005 moles per liter. Okay? So here's what I say on these. Do your math first and then do your units separately. Okay? So my math comes out to be 2.7 times 10 to the negative 4. Now I want to look at my units. Well, right off the bat, I know that minutes are going to be on the bottom. So I'm going to go ahead and do that. And so then I look at my concentrations, and I see that this mole per liter is going to cancel out with this mole per liter. But they're on the bottom, so now it's going to look like this. Liters times mole to the minus 1 times minute to the minus 1. Okay? All right. Let's do another one. In this one, when am I going to show you the ugly algebraic method? Oh, I'll do that after this one. Okay. All right, so we have A, B, and the initial rates. Okay? So when I look at this one, I'm going to find 2 experiments and see where they're remote saying about the same. And unfortunately, there is only one, and that is 1 and 3, where B is essentially held the same. Okay? So if I look at that one, this one and the, oops, if I look at this one, A and B, 1 and 3, I am multiplying that by 4. Okay? And when I multiply that by 4, I notice that my rate went up by 16. Okay? So you can think of it like this. 4 squared is equal to 16, right? And so that means that that is second order for A. Okay, so we know that A is second order. So now I want to look at B to find that one. And so that one, in that case, there's nowhere where A is held constant. But if I look right here, I see this is times 2, right? And so if I expected that, it should quadruple. But this is also times 2. Okay? And so that one I would expect either a doubling or quadrupling. And so then I look back here, and again, it's times 16. So that means that a quadruple and a quadruple gives me times 16 amount. Okay? So that's also telling me that B is a second order. Okay? So then that would be rate is equal to that. So rate is equal to K, A, B, both second order. So this would be fourth overall. Okay? So what I would do on that is once I see that it's fourth order overall, I would automatically go put my units down because I know how to do that because it's always going to be one less than the order. So I know my units are ultimately going to be liters to the third times mole to the negative third times second to the minus 1. Okay? So now I'm going to figure out my K value. So it's going to be, again, I just picked the top one because it's easier. Oh, that's just 5. So used to writing 10 times the negative on things, and I didn't realize that's just 5. And that's moles per liter times second. and that's going to be divided by 10.1 moles per liter squared and 2.01 mole per liter, and then that's squared. So when all of that is said and done, I'm running out of room, when all that is said and done, and I plug that into my calculator, I get 0.0121. So that is my final answer. Okay? All right, so I guess we're going to show you the ugly algebraic method now so that we can figure that one out. Okay? So sometimes it's necessary to do this. I would always try to do the table logic first, but if you have to do this, sometimes when things aren't held constant, this is one way you can do that. Okay? So in this case, what we would do is in this case we only have one concentration of reactants, okay? And so, yeah, you could look at that and figure it out, but we're going to just show you in case you need to use it this way, okay? So it depends on how you want to do it. I personally like whole numbers, so I will pick the trials in which I'm going to have a larger number on top. So I'm going to use experiment 1 and 2, but I'm going to put 2 on the top, just because I'm going to come out to a whole number instead of a decimal. So I'm going to do experiment 2 over 1. And so when I do that, I'm going to have the rate, which is 2.6 times 10 to the negative 7 equals K, and then 2 times 10 to the negative third raised to the x, because we don't know what x is, and then I'm going to divide that by the first experiment. So 1.3 times 10 to the negative 7 equals K, and then 1 times 10 to the negative 3x. So very cool. K is going to cancel out because it's the constant for the whole thing. So then when I divide 2.6 divided by 1.3, I get 2 is equal to, and I divide 2 to the negative 3 divided by 1 to the negative 3, and I get 2x. So that means that x has to be equal to 1, because 2 to the x to equal 2 needs to be raised to just the first power. Okay? And I just realized that I did not give myself enough room to figure out the rate, or the K, and so I'm going to erase all that. So hopefully you have that. So I'm going to erase those strokes and then figure that out. Okay? So our rate, we found it to be first order, is K times, let's just use A, so we don't have to write all that. Okay? So then K is going to be equal to the rate, 1.3 times 10 to the negative 7 moles per liter times minute here, divided by 1.0 times 10 to the negative 3 moles per liter. So a first order reaction means that the concentrations are going to cancel out. So my value for K is going to be 1.3 times 10 to the negative 4 to the minute minus 1. And then that would be the answer to that. Okay? So on this last one, I am going to stop the video here, and I want you to see if you can get the correct answer. So get the correct rate law and the correct answer, and then when you've finished it, then start the video back up. Okay? So you should pause it here so you can work this and see what you get. Okay? Okay, hopefully you got that. If not, we definitely need to answer some questions. And this is where this lesson is ending today.